All right. Let's just get this show on the road. I'm sick of waiting on this. So all right. So we're asking the tank. We have a tank full of water. It's a spherical tank with like a 1-inch neck. And we want to find the amount of work required to pump the water out of the spout. So our force function is just going to be, our work function is going to be force times distance, right? And our force is just going to basically be mass times gravity, right? Because gravity is the accelerant acting on this. So we know that's going to be 9.8. And now we need to find a way to represent mass and force in terms of some variable x. I'm sorry, mass and distance in terms of some variable x, right? So let's say we draw like one, bless you, like hypothetical cylinder. So like there's our hypothetical cylinder. So that's dx is the thickness of that cylinder. And then this is going to be the radius for it. And then we're going to need to be able to pump, like that distance, right? Does everybody feel okay so far? Okay. So I'm going to start by trying to rewrite this volume function in terms of like some x. Is that going to be the easiest x to use? Let's try it. So if I do that, my distance is going to be the whole height of the container, which is 6 meters, plus the 1 meter there. So my distance would be like 6 minus x plus 1. Everybody okay there? And now, like, I'm going to go ahead and think about that as a triangle. And gonna think about like this is a triangle. Those aren't similar though. I don't think I've picked a good X. So I don't see a good way to resolve these into the same thing. So I think I've done a poor job of picking my x. I'm going to take a minute here and just drop in the actual image from this now that my computer wants to cooperate. That is bigger than I thought I was going to get. Maybe I've just drawn the wrong triangles. Let me try that. Maybe that's the issue. Yeah, I bet that's it. What if instead we think about all right, I need help. Set up. What are we gonna do here? I don't see it. Where is this? I'm so frustrated. I'm sorry, guys. Oh, I see it. 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 I think. So this is like 3 minus x is that side. There it is. There it is. There it is. That's the triangle I need. I found it, Alex. I got it. So that's the radius. This side is 3 minus x. And this side is 3 because it's a radius. So I have then that 3 minus x squared plus r squared has to equal 3 squared. 9 minus 6x plus x squared plus r squared has to equal 9. So r squared has to equal 6x minus x squared. So I think that for my radius. Does that feel okay? I had to play around to find the right triangle. Okay, so the volume then for that cylinder is going to be pi r squared and then delta x. So the mass is going to be the volume times the density, and I know the density is of water. It was given to us in the previously. It's like 1,000 kilograms for 1 cubic meter. So this is my volume problem times my density. So my work then can be the integral from 0 to 6 of pi times 1,000 times 9.8 times that guy. Oops, I forgot my distance. Times would it be like x plus or x minus or 7 minus x. And I think that'll do it. Now textbook did something a little bit different here to orient theirs, but I think this should still work. Let's see if we get the same result. Oh, I'm not even going to bother with that. Shoot. It's the wrong button. So then I have, instead of writing it this way, I'm just going to write it as like 6x minus x squared. Where the squared cancels the square root. Fingers crossed. Oh, I sure did. Thank you. So I'm just going to do this. And they have 4 0.43 times 10 to the 6th, which is what I have here. So this setup worked. The textbook set it up differently. They did a weird thing where they oriented like 0 at the center of the sphere. So they integrated from like -3 to 3. I find that really like a puzzling choice. The way that I set this up is like just starting from the bottom up. Felt more natural to me, although I struggled to find the triangle there for a minute to be able to rewrite R in terms of X. But we got there. I just had to like look around for it the right way. Alex, did that feel okay?
Yeah.
I stumbled around a little bit there looking for the translation between radius and that distance, but once I found it, everything went along pretty smoothly, I think, right? So I'm happy that worked out. Paulo. 13. 6 point. Okay. Oh, that's not garbage. Yeah. Shells number 13. All right, so I want to start by sketching myself a picture of what's going on. And we're going to be by rotating the region bounded by the given curves about the x-axis. Okay. So far, so good. Okay. What is the graph of this thing going to look like? It's a parabola facing sideways. Is it opening to the right or to the left? To the right, because it's the squared part is positive. And the vertex of the parabola is going to be at 1, 2. And if I plug in like if I plug in 0 for y, I'm going to get 5 for x. Is that okay? You guys see that? So 1, 2, 3, 4. Well, let's do this. I'm just going to plug in 2 for x. That'll be easier. And we'll find the corresponding y. Why am I plugging in 2? Yeah, that's where it's going to intersect the other curve, right? So this is my shaded region, right? And rotating about the x-axis. So if we look at this like in 3 dimensions, let's see. it'll kind of look like this, I think, something like that. The issue is if we're rotating about the x-axis, if we tried to do a washer, the inner radius and outer radius would be on the same curve, right? So this is like a textbook shell problem. You see that? Okay. So when I draw this, my radius is going to be that distance, and the height would be like that distance. Does that feel okay there? Okay. So I'm going to be integrating along the x-axis because that's my axis of rotation. And then I need pi r of x times h of x. Does that feel okay there? And what are the bounds of integration going to be? 1 to 2 is correct, because that's going to be we're just moving along this guy. So I noticed that r of x is a y value and h of x is an x value, right? So the h of x is just going to be my function 1 plus y minus 2 squared. I screwed that. And my r of x is a y value and it's always going to be so I know this distance is always 1, right? And then my r will go from God, I'm having a bad day, guys. Do you ever start in the morning and just like your brain just is not functioning?
Every day.
Yeah, it's a bad day, guys. I just feel like I'm just lost inside of this.
I don't even want to do
All right. I'm going to go back here for a minute. So the picture is fine. So made a couple of mistakes though. So the variable in which respect I'm going to be integrating is the one where, you know, the radius is perpendicular to the x-axis. right? So that tells me we should be integrating with respect to y. So these should be r of y and h of y. Well, we have to rewrite it in terms of y's, though. Like, the function has to be in terms of y's. Yes, it's an x value because it's a horizontal distance, but we need to rewrite that function in terms of y's to be able to integrate it, which is okay because that's kind of what we got. So if I'm following my radius, what are the values for the or the bounds for that radius? Well, the shortest radius would go from like here to here, right? And the longest radius would go from like there to there. So I would say 1 to 3. Do you see that, Paulo? So the radius is just a y coordinate because we're starting and we're just counting up or down, which is fine. That's a good way as just y. So the h of y isn't going to be, isn't just x, right? Because x is that distance, right? What we want, or I'm sorry, this distance is 2, this distance is x, so my height should be 2 minus x, yeah. And the x in this problem is 1 plus y minus 2 squared. And now we got it. Two minus 1 plus y minus 2 squared dy. 1, 2, 3, 1, 2, 3. And that should be my setup. So how I got the radius and heights?
Yeah.
Okay. So I have this picture, right?
Yeah.
So this distance is r. That's just going to be at this point. This is like some x comma y, right? The r is just y, correct? Because it's going to this point on the curve, which is the point x comma y, correct?
I'm sorry, why is it like x?
Let's start at the beginning. Let me just redraw some of this. We'll do it all again in real time. I've got too much stuff going on. Okay. All right, so this is my picture, right? I'm going to draw like an arbitrary one of my shells or whatever. So like I'm going to go to this point up. That's my radius. And that point through the shaded area, that's my h. Okay? This point here is just some xy on the curve. Now, that y is going to be the same as my radius distance, because when I plot a point, I go x over and y up, correct? The radius is just up from the x-axis to the point. That's just a y coordinate. Does that feel okay?
Yeah.
And I know that this distance from the y-axis over to the point, that's my x coordinate. And this distance is 2. So the h has to be 2 minus the x coordinate. Does that feel okay?
Yeah.
And I know that the x coordinate is found by doing that. So that's my setup. Does that feel better
Yeah.
now that I didn't stumble my way through it so badly? We talked about it fresh from the picture. I apologize again, not having a great day. It's early, guys.
Yeah.
Who's next? Hmm?
Go over the 3 techniques, like just like one problem.
For the rational function stuff? Or the shell disk?
The bonus.
Mm-hmm. Yeah. Sure thing, dude. All right, so I'm going to just write up 3 examples here. And then we'll do each one of them, but I want to write down the 3 so we can talk about how we know which one is going to be which. Because I think that's, as much as anything else, can be a challenge. Okay. So these are 3 examples. So our 3 techniques were using synthetic division, or I'm sorry, polynomial division. Synthetic division is a type of polynomial. Using tan inverse, or using that partial fraction decomposition, right? So if I look at these, the Q for polynomial division is the degree of the numerator has to be greater than or equal to the degree of the denominator. We see that happening in A, right? For the tan inverse, what you're looking for is the degree of the numerator should be 0, and the degree of the denominator has to be an even degree. So that's what we see here. There's going to be a tan inverse one. And the last one is for the partial fraction decomposition. This is the most versatile one, but you need the degree of the numerator to be less than the degree of the denominator. And ideally, the degree of the denominator should be factorable, which is what we see here. So that's going to be a partial fraction decomposition. Is that helpful to just like, here's 3, look at them. How do I know what to do on which? Let's talk through that again. Okay. So for the partial fraction decomposition, we'll start by setting up our synthetic division. I know I can do synthetic division because the denominator is a monic polynomial, degree 1 with leading coefficient 1. So I'll set that equal to 0 and solve. I get 5. That's the number that goes on the outside. And then the coefficients from the numerator are the numbers up top. I bring that first number down, and then I multiply and then add. So we can say that what we get here is x plus 8 plus 45 over x minus 5. So far, so good. So that's what we'll integrate. So the integral, or the antiderivative of x is just x squared over 2. The antiderivative of 8 is 8x. And then to do the antiderivative 45 over x minus 5, that's going to be a u sub problem. So that becomes like 45 times 1 over u. That's like what we're doing the antiderivative of. So the antiderivative of 1 over u is the natural log. So I have 45 natural log, and then I'll put x minus 5 back in, and then I have my plus c, and I'm done. Paulo?
So for the test, we have to do these three. It's on the no calculus section. Are we doing the setup like that, or do you want us to?
This one will be I want you to do the integration on this and get all the way to the finish line. So that what I boxed is our final answer. And again, if you simplified the log part a little bit or whatever, that's fine, but you don't need to do that. So far, so good, Michael?
Yeah.
Okay. The next one is doing the tan inverse. To do the tan inverse, though, before I do that, I have to do a completing the square on the bottom. So I'm going to take that middle term, the linear term. I'll take that coefficient and divide it by 2 and square it. And if I'm adding it, I have to subtract it right after, because it's like doing nothing at all then. And then I still have that plus 11. So x squared plus 6x plus 9, that's a perfect square. That's x plus 3 squared. And then I have a plus 2 left over. So I've done the completing the square piece. Does that feel okay? Now, what's the problem, though, with the way that completing the square piece is written? Yeah, it's not plus 1 at the end, right? So what I will do is I'll multiply the top and bottom by 1/2. So I'm going to write that as 7 over 2. And I have 1/2 times x plus 3 squared plus 1 now. I have the plus 1, but what's the issue? I made a new problem for myself. That 1/2, right, is outside the squared. I need to push it inside the squared. So what squared is going to give us 1/2? How about 1 over the square root 2? Is everybody okay with that? So what I'll do is I can do that and push that inside the squared. And now I have it set up to where I'm ready to integrate. So I had 7 over. So that's going to equal, dx. The integral of 7 over 2, 1 over root 2 x plus 3 squared plus 1 dx. I'm going to u sub this. The u is going to be all the stuff in the squared. If I take the derivative of both sides, du dx is 1 over root 2. So du times the square root of 2 is going to equal dx. So this is going to become 7 over 2 integral 1 over u squared plus 1 times root 2 du. I'm just going to think about pulling that root 2 out front with the rest of the junk. And 1 over u squared plus 1, that is tan inverse. And I'll go ahead and substitute my x back in. And then the plus c at the end. Now, when we did the completing the square, if this guy was just a 1, you're ready to integrate, right? I only had that extra additional step because it wasn't equal, or that last piece at the end wasn't a plus 1. So keep that in mind. If it does come out to be plus 1, that's good news for you. That cuts, an extra rearranging step to kind of shoehorn this into a inverse tan situation. Michael, does that feel okay?
Yeah, so the numerator doesn't, the value of that doesn't matter.
The value of that doesn't matter because you can just pull it all the way to the front anyway. So, because the tan inverse is just 1 over x squared plus 1. So whatever that numerator is, you don't care. I guess if it's negative, then it's cotangent inverse. So you care about the sign, I guess, but whatever. Paulo?
I'm just confused about the 1 over 2. How do we get?
Well, like, I have this 1/2 out front, right?
Yeah.
So what I need to do is I need to be able to write that as something squared. So what squared gives me 1/2? Well, the square root of 2 squared. And now because these have the same exponent, I know that like an bn is ab to the n. Like that's an exponent rule. So that allows me to kind of cram those two guys together inside the same parenthesis. And that's what allows me to do like the u sub. Does that, you see that now?
I do.
As to, because before I can't pick x plus 3 as the u sub and have x and then have u squared plus 1 on the bottom. I'll have 1/2 u squared plus 1 on the bottom. I don't want that, right? That's not gonna, I can't u sub that and use tan inverse on it. Is that, you see it? What the issue was? Okay. All right, that was gonna be in my way, so I had to erase that. All right, the last one is the partial fraction decomposition one. This tends to be the longest process, although algebraically I don't think it's so hard. So I want to start by factoring my denominator. And what I want to do now is I'm going to rewrite this as these two having to add up to give me this, right? Everybody feel okay with the initial setup? First thing I'm going to do is multiply both sides by x plus 6 times x plus 1 to clear the fractions. When I do that, and multiply here, the x plus 6's cancel, and I'll just have a times x plus 1. When I multiply to here, the x plus 1's cancel, and I have b times x plus 6. And when I multiply over here, both of them cancel, and I just have the x minus 3. So far, so good. I'm going to distribute through my a and my b. Now, with the way we add polynomials, I know when I add ax and bx together, I have to get 1x. And when I add a and 6b together, I got to get negative 3. So I can say A plus B has to give me 1. And I have to say that A plus 6B has to give me negative 3. That's a system then that I can solve, right? So if I just say I subtract the two equations, let's do elimination, I'd get like negative B equals 4. If just I subtract the bottom equation from the top one. Everybody see that? We're just kind of like subtracting down. So B would have to be negative 4/5. And if I then plug that in to say the first equation, I get that A has to be 9/5. So we can say then this is equal to 9/5 over x plus 6 plus negative 4/5 over x plus 1. Just got to make sure that when you're solving for the A and B, you put them over the right fraction. Right? The most common mistake is switching which one is over which denominator, and that's going to give you the wrong answer. You can't screw that up. You have to be careful on that. I know it seems obvious, but it's an easy mistake to make when you're going and you're stressed out or whatever. All right, now that we have that, we're ready to integrate. So this integral is just going to equal and we can break that up into like 9/5 1 over x plus 6 dx plus let's say minus 4/5 integral 1 over x plus 1 dx. And those are both going to be easy u subs. I'm going to use just a different letter. So I have like 9/5 integral 1 over u du minus 4/5 integral 1 over v dv. And the antiderivative of those is just going to be the natural log. And that can be done on a free response section. There's no need to simplify that any further with your logs or whatever. If it was a multiple choice, you could combine that stuff together, you know, using your rules of logarithms, and you'd have like you could write it that way. Or put a big fifth root around the whole thing or something, you know, like, but whatever, you know, you're just talking about rearranging at that point. All the calculus is done in the boxed answer. But keep in mind on a multiple choice, they may present that solution and not, you know, they may do some combining with the logarithms or something afterwards. Is that okay though?
The u sub, do you want us to like always write that out?
I would love that on a no calculator section. If it's a calculator piece where presumably you could have typed the integral into your calculator to get the answer, no problem. But if it's an indefinite integral where you have to do it by hand, where there's no bounds on the integral, I would like to see that just for my, you know, usually I'm giving you a point for noticing the u sub and doing it correctly. And if you make a mistake there, I can give some partial credit if it's like, oh, okay, you tried to do a u sub, but you screwed something up. like that helps me when I'm grading to assess what you understood or where you made your mistakes. So that's helpful to me. I would love for you to do that each time you did a U sub, just to write the U and the DU for me. Is that good examples? And I think that these are on par with what you would see. I wouldn't give you anything more difficult than what we've done here. This partial fraction decomposition in particular is probably on the same level of something I would give you. So I don't think that's not too terrible. Like the system was easy to solve by hand. Yes, Nate.
Could you do like one of those probably setup problems? I just don't really get it.
Yeah, so you just want to do another volume of rotation. Yeah, absolutely. Let me grab one here from the textbook. I guess I should use this because they have. So the big first step is always going to be to recognize which method you want to use, and then which which variable are you integrating with respect to, and all of that jazz. So let's pick one of these. I was doing some yesterday with Aaron, and we found a good one. Aaron, what was we did one of these in the teens. Do you remember which one it was? I liked that one because there was a tricky thing that happened in there that I thought was a good one. 18? Okay. All right, so it says that we're talking about the stuff between y equals x, 0, 2, 4, and we're rotating about x equals 1. So this has kind of a lot of stuff going on. So let's start. Y equals x is just going to be one of those guys. Y equals 0 is just the x-axis. X equals 2 is there. X equals 4 would be there. And then we're rotating about x equals 1. So my region that we're rotating is that. So far, so good, Nate? It says about x equals 1. So it's the area enclosed by those curves. And then we're rotating about x equals 1. So just from the direction there, right? You see it? Okay. So the first thing I want to do is decide whether this should be done as shell, washer, disc, right? So the first thing I'm going to notice is that I know it can't be done as a disc because there's the shaded region isn't touching the axis of rotation, right? There's a gap between there. So I know I'm either going to do this as shells or washers. So far, so good. Won't be discs. Now, what I do is I always want to assume, let's check to see if I can do it with washers because I would rather do that than shells if I can. So if it's done by washers, my inner radius would be from the axis of rotation to the first part of the shaded region. And then my outer radius would be from the axis of rotation to the outer part of the shaded region. Since those are different curves, I can do this as a washers problem which is what I would prefer to do. So far, so good? Now, the other thing I notice about this is that what I just drew, that inner radius is a constant, right? That's just 1 unit. And that outer radius is a constant. That's just 3 units until I get to this point, right? In which case now the inner radius is variable. Do you see that? Well, like now if I draw my inner radius, after that point, the inner radius length is changing, right? It's a different length everywhere after. So I know that I'm going to be chunking this up into 2 separate integrals. One where the inner radius is constant and one where it's variable. Does that feel okay? Okay. Since this is a washer problem and the axis of rotation is vertical, I know we're doing this with respect to dy. So this first section is going from 0 to 2. And then my formula for washers is R outer squared minus R inner squared. And since it's constant, there's no variables in there, I'm done. So far, so good?
Wait, how did you do 3 squared minus 1 squared?
So this is like R outer, and that's like R inner. Those are constants. The formula is just pi R outer squared minus pi or R inner squared. That's the formula for washers. So far, so good? Okay. And then the other section where the R inner is variable starts at 2 and ends up here at 4, correct? So the R outer is still 3 squared, right?
So R inner.
Well, R inner is going to be this distance, right? So I know this is 1. This distance is x. So this distance here is going to be x minus 1. And there's my setup. Yes. Oh, yep. Sorry, x and y are the same thing in this, right? Because x is equal to y.
Oh.
So I'm sorry. Yes. Very good. Thank you.
So there's like a formula for each method?
Yeah. Yeah. So disk is just pi r of x squared dx. Washer is like pi r outer of x squared minus r inner of x squared dx. And I'm going to just write of x. It could be y's also, right? And then shell is pi r of x times h of x dx. So those are like the 3 formulas. Again, this is just like a circle, right? This is just, like big circle minus little circle. And this is like surface area for a cylinder.
So it's touching.
Ooh, this is 2 pi r, excuse me.
So the area that you're doing touches where you're rotating using this.
Yeah, so if we had this exact same problem, but instead of saying about x equals 0, and we just had about like the x-axis, where it was doing this. Let me pick a different color. Now notice that my shaded region just touches the axis of rotation the entire time. This is just going to be a disk. Right? There's no concavity to it. That's the other thing I'd have to be careful about. You know, it's like if this thing went and did like that. Oh, I guess disks would still be fine. But that's what I'm looking at, because now when I do this, it's just basically going to be, you know, something like this, and every cross section I do is just a circle.
How do you know your respect to x and y is it like the axis?
Yeah, so for so these two, it's going to be dx if our axis of rotation is horizontal. And then here this will be dx if our axis of rotation is vertical. Does that feel okay? So the way I usually think about it is just like when I'm drawing this, my radius that I'm drawing are just going to be, I'm going to be moving vertically. So I know it's going to be dy. If I was going this way, like when I draw this, my radii are moving left to right, so it should be dx. And that's the same thing for shells. You just look at how your radii, how you're moving your radius, and that'll tell you whether you should be doing dy or dx. Like, I'm a visual guy, I'd rather not memorize it. But like if you're a memorizer, like that'll do it for you, you know. So the shell is just the opposite of the washers in terms of dy or dx. Is this helpful, guys? Kind of rehashing some of these little finer points about like what to do. Like that's typically going to be the hardest part here. Like just figuring out like which setup am I trying to do here. And even if you bungle it, if I can tell you're doing the right setup, like that's a point. You know, choosing the right thing and then having the setup completed, you know, like a point for your radii functions being correct or your height function being correct or whatever. Like there's a point for that and a point for the bounds, and you know, so there's ways to not get it right and still walk away with some points from the problems. Yeah, Paul.
For the MCQs in the calculator section,
Yes.
would that be just a mixture of all the sections, or?
Yes, I would expect to see some volume of rotation problems where we're looking for a specific answer, where you can do the integration on your calculator. I would expect to see some area problems. I'd expect to see average value problems. I'd expect to see like an accumulation problem. So I tried to be, you know, and expect to see one of these rational function problems. So I tried to be pretty fair in terms of like where I pulled these problems from, in that I got stuff from each of our main topics we focused on, like a question or so. Is that okay? Lucas.
Can you do 14 from 6.5?
6.5, number 14. Sure, hope so. I've not had a good track record so far, though. Okay. So it asks for the average value of f on the interval from 0 to 8. So I know that f av is going to be 1 over b minus a integral from a to b f of x dx, right? So that's going to be 1 over 8 minus 0. And then to calculate the integral of f of x dx, I'm just going to count the area under the curve. So I'm going to have negative 1/2 for this, positive 1 for that. I have this triangle, so that's 1/2 times 1 times 2 plus this square, so that's 2 squared. And then I have like this trapezoid, 1/2 base 1 plus base 2 times height, and then plus the next trapezoid, that's 1/2 base 1 plus base 2 times height, and then I'd be just grinding that out. There's no like sneaky way to do it other than just like finding the area under the curve kind of thing.
Yeah, I realized about halfway through that, I meant to say 14.
Oh, okay.
You're good.
Says find the numbers b such that the average value of f of x equals yada 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 on the curve 0 to b is equal to 3. Okay, so if I'm doing 14, I have that 3 should be equal to 1 over b minus 0 times the integral from 0 to b of 2 plus 6x minus 3x squared dx, right? So I'm going to do that integral. So that's going to be 2x plus 3x squared minus x cubed from 0 to b. So far, so good. And then I can evaluate that. So I have 1 over b times 2b plus 3b squared minus b cubed minus 0 plus 0. So I distribute the b down, or the 1 over b through. So 3 equals 2 plus 3b minus b squared. That's going to be a quadratic. I'm going to get everything onto one side. So I have b squared minus 3b plus 1 equal to 0. And then I just do the quadratic formula from here. So I have 3 plus or minus root 5 over 2. Does that feel okay? So just like, again, I just used what they told me to set up my equation and then just kind of grinded my way down. As long as there's one variable in there where I'm just solving for b, I figured I was going to be able to get it, especially with the function being a polynomial. I felt like, okay, this is just going to turn into solving a polynomial, which between me and my calculator, we can usually handle pretty well. But the initial setup, again, all I did was like write down what it said. It said this is equal to this. Okay, use my definition or my formula for average value and just set that equal to 3, and then just kind of grind away until I get an equation in terms of b that I can solve. Bless you, bless you. Yes?
For the test, do you think like for 6.4, the 6.4 problems, do you think it's going to be similar to like the one in the book? Or
No.
Okay.
No, I would look at the accumulation problems, the FRQ problems I gave you, or the scan through the MCQs and look for the accumulation ones there. I will not have something as nasty as like, how much work does it take to pump the volume out of this like crazy shaped container? Like those are hard.
Yeah.
Like it's good. Like those are good problems to do. Like they really stretch you, but like asking you to do that in a time test setting is rough. You know, like I tried to pick something that like it's not contingent on your three-dimensional visualization, your geometry skills, and like, look at,
I was just wondering.
yeah.
These are like weird.
Yeah, some of them are real hard.
Yeah.
The setups are real hard. You know, like I thought 2 was a really good,
Yeah, no, it was.
fair example of like what I would ask you to do. So, yeah. What's up, Ryan?
Could you help me understand this in 15?